So welcome to this class. The last class we just introduced the parameters which are important for the for running a atom probe needle in a atom probe tomography and during field evaporation, and also we discussed about the resolution. So we ended the last class discussing with some parameters which are responsible for determining the mass resolution. Now those parameters are, as I told you, these are pulse fraction, the second one is temperature, the third is voltage, and the fourth one is the tip geometry. Okay, so these parameters, if it is not optimally used, it might possible that even in the laser pulsing your mass resolution will be much poorer than the voltage pulsing or the HV pulsing. Okay, so this particular mass resolution, actually it can be modeled by Gaussian function. Okay, and it can be written as m by delta m, which is equals to 1 divided by under root of sigma v divided by v square plus 2 sigma t divided by t whole square plus 2 sigma l divided by l whole square. So I will just briefly describe these three important terms. Okay, so the first term is related to voltage, the second term is related to time of flight, the third one is related to the flight path distance. Okay, so this is called TF, time of flight distance. Okay, and there is another term which has to be added here, plus f of pulse with TD. Okay, so we will describe this term also. So this f pulse TD is the function that accounts for the loss of resolution associated with the pulsing mode and at any instant TD, okay, of the departure of ion from the surface. Okay, we will explain this term little bit more later. And the first terms in all the three, these are sigma v, sigma t and sigma l. These are all standard deviations. Or the errors in the measurement of voltage, time of flight and flight distance. So these all three contributes to the broadening of the or affects the mass resolution. Okay, so in the new APTs, the accuracy of time measurement is now better than 100 picoseconds. Okay, and the voltage, this is related to your time of flight. Similarly, the voltage supply is stability of the voltage supply can go up to a few volts per 10 kV. Okay, and related to the flight distance, it is better than 1 mm in modern detection system, which is having a 90 to 250 mm of flight path. Okay, and these effects are linked to the field evaporation. Okay, and this field evaporation and also this particular function, which is dependent upon either it is HV, either we are using HV pulsing or whether we are using laser pulsing. We will talk about the HV pulsing. Okay, so in HV pulsing, as we also discussed before, that not all the ions acquire the whole energy. it means related to your energy deficits. Okay, and this particular thing can actually induce spread in velocities of the ions, and due to which there will be a spread in the time of flight. So there will be a difference in the time of flight, and this can be corrected by energy compensation devices. Okay, in the laser pulsing, the spread in time of flight, is due to the cooling rate or due to the slow cooling of the thermal pulse. How we can improve? This can be improved by using different parameters, okay, such as wavelength of laser which is used, pulse duration, and also the focusing. Okay, so for faster cooling, if you want to do cooling of the faster cooling, actually we need to make the thicker specimens or with a high Shank angle in the case of laser pulsing, correct? This particular case is not for the HV pulsing. Fine. So there is a difference between the HP and laser pulse, and this is how we can improve the mass resolution. Okay, so in HV pulsing, mass resolution can be improved by energy compensation devices, and for in the laser pulsing, actually it is more dependent upon the parameters, mostly the wavelength, pulse duration, the focusing of the laser spot we discussed in the I think few classes before, and also the faster cooling by making the samples thicker or high Shank angle, correct? So now next topic we will cover is the how an element is identified. Element identification means how we can determine the element or composition. Okay, so how to identify? First we will talk about the element identification, then we will go to the compositional measurement. Fine. So in elemental identification, so the mass in the mass spectrum, it is nothing. You will get a relative number of atoms of each species present is analyzed in the analyzed volume. This information you will get from the mass spectrum. Okay, so identification of these elements can be done by identification, by defining the ranges of that particular M or the mass to charge which is corresponding to the each element. So now you have a mass spectrum, you have M, and you have number of ions. So if there is an appearance of peak, then actually you can range this particular region. Okay, this particular region can be ranged so that the number of ions can be calculated from this particular spot to this particular spot. So there is a increase in the peak, starting of the peak or onset of the peak, and there is also a onset at the back, correct? So this way the from the mass spectrum you will get the relative number of atoms of each species which are in the analyzed volume, and this can be defined as the range of M for each element. Okay, so identification involves the first is the position in the mass spectrum. or at which mass to charge ratio the peak is appearing, position in the mass spectrum. And the second important point is identification is the distribution of its isotopes. Distribution of its isotopes. Okay, and remember, as I told you, these isotopes, they have a certain abundancy in nature, correct? Based on the abundancy, these isotopes, so the isotopic ratios are usually maintained with some exceptions. Okay, so these isotopic ratios are maintained. So to for identification, these are the two important things which we need to take care. Okay, so the peaks which are associated with the minor isotopes, so if as I told you, if in some of the isotopes in abundancy they have very low values, it's like 0.2% or 0.1%, it might possible that that particular peak can be hidden in the background. Can be hidden in the background or overlap with the larger abundant or the larger abundant peak of the isotope, correct? And the charge state in which an element is detected, the charge state in which that particular element is detected depends upon the two parameters. The first is evaporation field for that particular isotope, EF value, evaporation field, and the second is the curves of the relative abundance of different charge states. Okay, and this is derived from the post-ionization theory. Okay, so this is nothing but what I told is abundancy. So they will maintain a certain isotopic ratios, and the charge state, which is the charge state of the element which is field evaporated, depends upon the evaporation field and also the curves of the relative abundance of each charge state, which is which is according to the post-ionization theory. Okay, in sometimes you will also get complex ions. Okay, and these complex ions, these are the actually ions consisting of the number of different atoms, the number of atoms that are encountered in the AP atom probe analysis. Okay, it might be molecular ions, it might be complex, or it might be cluster ions. Okay, so these are the complex ions. So this may involve one, so it means this particular statement means these ions may involve one or more species, or you can tell as a atomic species. Okay, and also we need to understand that the elements with several isotopes with several isotopes can form molecular ion. Several isotopes, elements with several can form a molecular ion. These ion comprises combination of individual isotopes. Okay, so it means that two types of isotopes can come together and can form a molecular ion and can be field evaporated and can be detected Fine. As an example, this is a very good example of SB. Correct. You can see that there is an appearance of a peak at 121. So SB 121 plus 1, and also there is a peak which is contribution from SB 242 plus 2. Correct. And there is an additional peak which corresponds to SB 121 plus SB 123 2 plus, which corresponds to this particular peak. Okay, so it appears at 122 dA. This particular peak occurs by the combination of the two different isotopes of the same element, which they are field evaporated as a one molecular ion. One molecular ion. Now the next topic which we'll touch upon is the range files. Just briefly I will introduce the range files. Okay, so range file, so as I told you, these range files, if you index it on the mass spectrum, if you index these range files, these range files is populated, and the lower and the upper limits of each mass range is taken care. Okay, and each mass peak is labeled with that particular element isotope or the ion or the ion or the cluster ion. Okay, so these are the range files. Okay, once we index it, then we need to find out the composition. Correct. Now the composition, so we will talk about the measurement of composition. Measurement. So after the identification of the element, first we have identified the element, by the mass range. The composition actually is computed from the proportion of atom of each species. So usually it is a proportion of atoms of each species. Okay, so if there is a J element, okay, which is a part of a multi-component alloy, or material containing I different species or elements. Okay, so if there is a J element which consists, which is a part of a multi-component material or alloy, where these are the I with the I different elements, so the composition can be given by Cj in atom percentage is given by minimum to maximum NAT divided by summation of all the elements with their M minimum mass to charge ratio minimum to mass to ratio maximum of NATM into 100, which is nothing but you can put it as a N atom percentage of that particular element, J element, divided by N total number of atoms into 100. Okay, so this is how the composition of that particular element, J element, can be measured. Okay, so here the NAT is the number of atoms at that number of atoms or the ions at the mass in the at the mass to charge ratio of M in the mass spectrum. Okay, and I is the each element by its range each element between the range of m mass to charge ratio minimum to the mass to charge ratio maximum. Fine. So this composition is nothing but the atomic ratio. Okay. So now there is a volume, there is a particular volume which is analyzed, and you are measuring composition of a J element in an alloy which is having a I number of components or I number of elements. Okay, so it is actually related to a statistical distribution. Statistical distribution or statistical distribution. So it will induce a statistical variation of like sigma j for that particular element in the composition, and this statistical variation can be given as sigma j is equals to root of Cj 1 minus Cj divided by total number of atoms. Okay, so this is called, this is just related to statistics, or we can tell is a statistical variation. Correct? Fine. So I hope now the composition measurements, you understand that how composition is measured for that particular element in a multi-component material with a different with total number of elements present, or I different types of elements present. Okay. So the next thing is the detectability. Correct? We'll talk about detectability. So it is nothing but the ability to detect a given atomic species. Okay, so this depends upon the statistical variation. Okay, so so it is nothing but to measure the composition of an element. So for example, if you are measuring a composition of an element, which is at a concentration of 200 ppm with a precision of 50 ppm. Okay, then for this particular thing you need to collect the more than 100,000 atoms should be collected. Okay, so this depends upon the statistical variation. So that's why in very dilute systems you need to have a total number of atoms which are detected should be very high. Fine. Another thing is the detectability depends it can be mass resolution and the signal to background ratio. Okay, so why it is important? Because in a mass spectrum, if you have a certain background and if your peak is small enough that this is your mass peak, and the peak of this particular mass spectrum if is equivalent to the background, then the composition then it cannot be detected. Okay, so a peak can be distinguished only if the amplitude, if its amplitude is greater than the background level. Okay, so these are the two important things which usually it affects the detectability. There are other parameters which are also affecting the detectability. One is flight path. Okay, so flight path. So some of the APTs, some of the atom probes, they actually we can vary actually the specimen, the distance between the specimen and the detector. This particular distance can be varied. So due to which actually we can get a higher mass resolution. Okay, due to which we can increase the mass resolution by increasing the actually time of flight. The only thing is if you reduce, if you increase the flight path larger enough, then you are inducing the lowering of field of view. So it has to be at a optimum distance. Lowering of field of view. Okay, so this is the importance of the flight path. Now we will come to the two important more parameters which is related to your pulse fraction and temperature. Pulse fraction and temperature. So the electric field which is required to induce the field evaporation at a given rate of evaporation rate, is critically depends upon the temperature of the specimen surface. Okay, so the intensity of the electric field which is required to induce the field evaporation for a particular evaporation rate at a constant rate, then it critically depends upon the temperature. Okay, and this influences the microanalytical capabilities of APT, or we can tell it as a microanalytical capabilities of an atom probe. Okay, so when the specimen contains atomic, so this, if you have a specimen, it means that if you have a needle specimen with different components or elements, having different evaporation field, so the temperature should be chosen in such a way that it should be you can actually detect detect all the ions together, correct? So your the required electric field totally depends upon your temperature. This can be understood by the stabilization curve. So now you can see that if you see this particular graph, okay, so in this graph, this is your field, electric field, this is your temperature. This is nothing but a calibration curve, correct? So this is the field temperature. Okay, so example in this condition, so you can see that the field evaporation should be directly triggered by HV on the laser pulse. Either you do HV or you do the laser pulse. And the time of HV. Okay, so you are applying a DC voltage to the needle specimen. Fine. So this DC voltage should be enough to avoid field evaporation between the pulses, correct? So you are applying a pulse, so the DC voltage should be enough such that to avoid the field evaporation in between these two pulses. Okay, so the two parameters important are the base temperature and the amplitude of pulse field. For either for the so in the case of HV it is a voltage. In the case of thermal pulsing it is the temperature. So first we will describe in the case of HV pulsing. First we will talk about the HV pulsing. First we talk about it. So the pulse fraction has to be adjusted in such a way that you should avoid the preferential departure or retention of any given species in the specimen. So if you have a specimen, correct, and these specimens, if you see that if some species have a different evaporation fields, so your HV pulsing or the pulse fraction should be such that you should avoid, the first is preferential departure and also preferential retention of any species during the HV pulsing. Okay, this will have a direct impact on the composition which is of that particular volume which is to be analyzed. Okay, so in this so you can, if you see the plot, you have a, in y-axis there is a field, this is the temperature, okay, and F1, F2 and F3 are the DC are the fields, the minimum fields which is applied on the tip surface. Okay, so if you talk about the condition 1 and condition 4, okay, you can see that this dark region. So if you see that when you apply a HV pulse, okay, so this is called pulsing, you are increasing the HV pulse, then okay, so you can see that it covers the phi 1, phi 2 are the evaporation rates, okay. So this first and fourth case are the best or the good analysis condition, where both A and B species have been avoided preferential departure or preferential retention. So both the A and B species can be field evaporated in a specific evaporation rate. Okay, so this particular curve, you can see that if you apply a pulse from F1 to up to a level of this, then you can see that you are covering up both A and B, both A, this is B, and A during that pulse event, where these can be field evaporated at that evaporation rate. But if you see the second one, okay, you can see that the field required or the field required for the A is much higher, okay, for the field evaporation to takes place. So you are putting a pulse from F2 to a level where only B can be field evaporated. So actually you are putting a preferential departure of B atoms. Okay, so or what we can tell is that what we can tell is that in the second case you are not reaching the field which requires to field evaporate A species. So actually what you are doing is you are doing preferential retention of A atoms, and you are getting B atoms more and more field evaporated. So your composition will change according to that. Correct. Now in the case of third case, where you are applying a pulse from F2 to a level more than A, but what you can see is your main F2, the base DC voltage, is more than F2. Okay, and you can see this particular line B, it is lower than the base DC voltage. It means that on application of, without any application of pulse, actually you are continuously field evaporating the B atoms. It means that you are doing the preferential departure of, you are provoking or the preferential departure of B atoms for the condition of 3, where your base DC voltage is more than the field evaporation evaporation field of the B atoms, if you want to make a phi 1 evaporation rate. Okay, so I hope this you understand that how pulse fraction and the temperature are very important, so that you can get and how it is controlled, how it can affect the composition, or we can tell is the detectability of these different species which is having a different evaporation fields. Okay, so in this only the case 1 and 4, these are the optimum conditions where actually only on application of pulse these A and B species are field evaporated depending upon their evaporation field values at that constant or the evaporation rate. Fine. Similarly, in the thermal pulsing, similar thing can be understood, but only thing is in thermal pulsing you are actually changing the temperature. You are inducing the increasing the temperature as a thermal pulse. So the only difference will be in this direction, in horizontal direction. Fine. And but the conditions will be remain same as for the HV pulsing. Okay, so for thermal pulsing the condition is it will be the same scenario, but the arrows would be horizontal. Okay, so so with this what we described is the role of the importance of pulse fraction and the temperature, which can directly affect the composition of that particular alloy, which is having the components or the species with different evaporation fields. Okay, so the correct analysis condition is should be an equilibrium point. An equilibrium point means the combination of pulse fraction and temperature. It should reach that all evaporation fields and temperature. Okay, so in thermal pulsing, the DC field is lower than the HV pulsing. Okay, and usually the DC field required in thermal pulsing is lower than the HV pulsing, because you are inducing the temperature, increasing the temperature, so makes more preferential evaporation less likely. So only this problem with the composition or the preferential evaporation or retention is more will found in HV pulsing other than the thermal pulsing. Okay, so with this I will end this class now. I hope you got a good feel about the importance of the pulse fraction and the temperature and how this affects the composition. So these are the parameters which are important during the running of the atom probe of that particular sample. So with this I will end this class. In the next class we will come to more parameters which we can fine tune for better analysis. Thank you.